Hello friends. Today let us take one example where the integration is given over this region R, and R is the area between these two circles. Okay. Now we should understand first of all the geometry of these circles. So let us find out what these circles are and how we can uh, draw them on a paper. So to draw these circles, we need their center and radius. So the center and radius can be easily obtained by using the completing squares method. Okay, so I take the first equation and I try to complete the square. Okay, so x square plus so this is minus ax, right? So this is the middle term, right? So I'll add one more term over here, and that is plus a by 2, okay, square, minus a by 2 square, okay, plus y square equal to 0. So this is a completing squares. So what you do is you take the middle term, the coefficient of the middle term, divide it by 2 and add and subtract its square. Okay, now you observe this part. Okay, so this part is ax minus a by 2 bracket square, right? Then I'll write y square and I'll send this over here. This is a by 2 square. Fine. So now we can compare this. So this is x minus a bracket square plus y minus b. So I can say y minus 0 square equal to r square. So this is a circle centered at a by 2 comma 0. So that is on x axis, and radius equal to a by 2. Right? So now we can easily draw this circle. Similarly, if you observe this circle, so similarly I say if I make a completing square method, okay, this is 2a is a term, so I'll make half of that, that will get a, so I'll add and subtract a square. Okay, now say this part is a complete square, so x minus a bracket square plus y square is equal to a square. So now you see that easily, this is a circle again centered at a comma 0 and radius is a. So center at a comma 0 and radius equal to a. Fine. So now we can draw these figures. Okay. So let us draw these figures over here. So that we can easily visualize the area tracked between these two circles. So this first circle is a, so I'll take here as a by 2 comma 0, and this is say a, or let me take this axis over here. Okay, so this is origin. This I'll take as a by 2 and this as a, suppose. Right? So the first circle is centered at a by 2, and of radius a by 2. So this is a circle like this. Okay, so this is circle 1, and then centered at a and of radius a. So that circle will be like this. Right? So this is a smaller circle, this one, and this is a bigger circle, this one. And now we require area between these two. So this is the required area. So this is the region R on which we are integrating this particular function. Okay, right? Now see that I told you in the last lecture that whenever they involve y square term, okay, you always try to convert the given equations into polar form, okay, because that becomes very easy to solve. So this picture we have obtained now, that is a picture of this region A R, right? Now we will proceed by converting this problem to polar form. Okay, so how you convert the given problem to polar form? It's very simple. There is only one substitution. You put x equal to r cos theta, y equal to r sin theta. Okay, so I'll say let let x is equal to r cos theta, y equal to r sin theta. So this is a very standard substitution to convert the Cartesian form to polar form. Okay, and then I told you that dx dy will be r dr d theta. Fine. Okay. Now what happened to these equations of these two circles? So if I substitute here in the first equation, what I'll get is, so circle 1, I say circle 1 becomes r square cos square theta plus r square sin square theta minus ar cos theta equal to 0. So see, I have substituted all these things. Now this is what? This is r square equal to ar cos theta, right? And so r get cancelled, one of the r get cancelled, and the circle equation becomes a cos theta. So this is the equation of this circle in polar form. Okay. Similarly, you can obtain the equation of this circle in polar form. Okay. So circle 2 is, so I say similarly, circle 2 is r is equal to 2a cos theta. Okay, so this way you can obtain the equation of the two circles in the polar form. Okay, now to obtain the limits on r and theta. Okay, you see that now. See, this is your r vector always. It starts with origin and it goes like this. This is the r vector. Okay, so to cover this region, you look at this r vector. So this is my pen. This pen is the r vector. Okay, now at the lower part, it intersects the circle here, and to the upper part it intersects the circle here. So these points are equal to a cos theta to 2a cos theta. So when I am going to write down the limits now, see, the limits for r will be from r equal to a cos theta to 2a cos theta. Why? Because this radius vector intersects at lower end to the a cos theta circle, at upper end to the 2a cos theta circle. And now I want to vary this theta. So this theta is actually varying from pi by 2, minus pi by 2 to plus pi by 2. See, this is minus pi by 2. This is plus pi by 2. Okay, so I am varying it from minus pi by 2 to plus pi by 2. Right? So inner integration limit with respect to r, outer will be with respect to theta. Now inside y square, so y square is what? It is r square sin square theta. Okay, into dx dy. Dx dy is r dr d theta. Right? So now we will solve this. Fine. So this is equal to, further, this is minus pi by 2 to plus pi by 2. Okay. A cos theta to 2a cos theta. Now this is r cube dr, and then we'll write sin square theta d theta. Okay, fine. So now this becomes r raised to 4. So this is minus pi by 2 to plus pi by 2. R raised to 4 by 4, running from a cos theta to 2a cos theta, sin square theta d theta. Okay, right. So fine. Now let us substitute the limits. So this is further equal to, now this 1 by 4 I'll take outside, minus pi by 2 to plus pi by 2. Okay, now if I put it here, it is 2 raised to 4 is 16, a raised to 4 cos raised to 4 theta, okay, minus a raised to 4 cos raised to 4 theta into sine square theta, okay, d theta, right? So this is 15 a raised to 4, so I can take that 15 also outside. This is 15 by 4 minus pi by 2 to plus pi by 2, okay. A raised to 4 also we can take outside, it's a constant, and we left with cos raised to 4 sine square, cos raised to 4 theta sine square theta d theta, right? Now you see that this is a even function, okay. So by using the properties of definite integration, we can write this as 30 or 15. So 2 into 15 a raised to 4 by 4, integral 0 to pi by 2, cos raised to 4 theta sine square theta d theta, right? So by using the properties of definite integration, so this is 15 a raised to 4 by 2 now, okay. And now see that here we can apply the rule that we have learned, okay, in the nth reduction formula. So what is the rule? So both powers are even, right? And it is running from 0 to pi by 2. So n minus 1, 2 minus 1, 4 minus 1, that is 3, and 3 minus 2 is 1 again, divided by 4 plus 2 is 6, 6 minus 4, 6 minus 2 is 4, then 4 minus 2, that's it, into pi by 2, finally, right? So this is n minus 1, m minus 1, okay, n minus 1, and m minus 1 is 3, 3 minus 2 is 1, so this is 1, then 4 plus 2 is 6, 6 minus 2, so 4, and 4 minus 2, right? Okay. So now this is equal to 15 a raised to 4 by 2 into, this is 1, 3, so 3 pi divided by 6 into 4 into 2, 6 into 4 into 2 into 2, okay. So if we simplify this, what we will get is 15 a raised to 4 by 64, okay, and that's correct answer. Yeah. So I hope you have understood this. So getting a region and then converting it to the polar form and then solving. Okay. So this is a very difficult problem. Try to solve some more problems from the exercise.